All right, this is Physics 1C for March 11th. Let's make sure we're good. And today we're going to talk about electric potential. We introduced this idea yesterday, and we're just going to do some more problems. The first of which is right here on the screen. So let's just kind of remind quickly what we did last time. So what we did is we said that for a point charge, that you could calculate the electric potential by basically doing this. You take the charge times Q, and you divide by the distance. Electric potential is a scalar. It's measured in volts. And, yep. Okay, so we want to do this problem right here. It says an electric dipole consists of two charges of equal magnitude and opposite signs separated by a distance 2a. So that's what's going on in this picture right here. The dipole is along the x-axis and is centered at the origin. We want to calculate the electric potential at a point P on the y-axis and then at a point R. And then we're going to use that to find the electric field, because the other thing that we learned last time is that if you know the electric potential, you can find the electric field at any point really by taking the gradient of the potential. Okay, so let's go through it. All right, first of all, at point P. So to find the electric potential at this location, what we care about is basically the distance between, maybe I can make this picture just a little bit bigger. We need the distance between the charge up to the point in both cases. So let's write what that would be now. So the electric potential is going to be equal to K times the positive charge Q, and then divided by the distance between Q and P. So the distances that are given on the picture are A and Y. So the distance between Q and P with a Pythagorean theorem we can say is just A squared plus Y squared square root. And then for the negative charge, which is on the right, you're going to have K times negative Q divided by the same distance, A squared plus R squared, or Y squared. And then that's pretty clearly equal to 0. These two cancel out, right? Any questions about that? Okay. For part B, we want to calculate the electric potential at a point R on the x-axis. This one will not be 0. So we're at the point R, which is a distance x from the origin. And we do basically the exact same thing. We say for the positive charge, it's going to be K times Q. And then we got to divide by the distance between the positive charge and point R. So that's going to be x plus A. And then plus K times negative Q. The negative charge, the distance is x minus A. That would be this distance from here to here. And to some extent, that's the answer. We can simplify it a little bit, though, because we could factor a K and a Q out, and then we would have that. And then we can simplify what's inside of here, like this, and get a common denominator. So if I multiply x minus a up here.
There should be a negative for the second term, right?
Yep, thank you very much. Multiply the x minus a up here, and then the x plus a over here. So this will end up being minus x plus a. And then the common denominator will be x squared minus a squared. All right. And then, yeah, we can simplify the numerator because we'll have, let's see, it's going to be the x's that cancel, I guess. X minus x, right? And we'll have negative 2a, I guess, in the numerator. So it'll be negative 2a. Does that look right? Anyone have any questions? Does it make sense that it's negative? X is definitely greater than A, right? So the numerator is going to be, or the denominator is going to be positive. Does it make sense that the potential would be negative?
Is it because it's closer to the negative charge?
Yeah, exactly. If we were to switch these two charges around, my guess is that the answer would just be positive, but you get exactly the same result, basically. Okay, so that's the electric potential at point R. I could have said that this is the potential at P and this is the potential at R. All right. And the next thing we want to do is to calculate the electric potential and the x component of the electric field at a point on the x-axis far from the dipole, right? So I guess there's two different ways to do this. One way would be to basically, I guess we just do it both ways and see if we get the same answer if you all want to. So one way would be basically to take the limit of this expression here as x becomes much, much larger than a, and that would give us the potential. And then what we could do is we could use that, basically take the derivative to find the electric field. Or we could take the derivative to find the electric field and then do that. So let's just do both. I think you should get the same answer either way. So as x becomes much, much larger than a, what is this term right here going to reduce to? VR.
X squared.
The denominator will go to x squared, right? Because this term will just be bigger than this one. And since they're subtracted, there's nothing wrong with just making a squared 0. Now, the one in the numerator, we can't just make a 0, right? Because it's a ratio. So we'll get negative 2k times q times a divided by just x squared. And now if I want to find the electric field at that location, what we have to do to find just the x component, we have to take the negative partial derivative of VR with respect to x. Again, a partial derivative just means that you're going to hold every other thing constant. Every other variable that might show up is going to be a constant. So taking the derivative of this and making it negative, we're going to get the derivative of that would be x cubed. You have to pull down a negative 2 in front, right? So there's a negative sign overall outside. From the denominator, for the power of x, you're going to get a negative 2. And that's multiplied by negative 2 kqa. And all of that then is divided by x cubed, I think. Does that look right?
Mm-hmm.
Sorry for all the parentheses, but it's a lot of negative numbers. Okay, so 3 negatives mean we'll get a negative. So it's going to be 4 negative. Oh, I left something off here, right? There's still an a. So negative 4kqa over x cubed. We calculated this just using electric fields before, and we got the same 1 over x cubed dependence, although I think the one we did had the positive sign and the negative sign switch. So I think we got a positive number, but same result, basically. All right, any questions about that?
Hey, Professor, could you remind us why it's a negative partial?
Why it's negative? It's basically, it comes from the fact that the connection between the force fields and the scalar fields is related to the connection between change of potential energy and work, right? Basically, this is where it all stems from. That when you have a conservative force, the work done by the force is equal to the negative of the change of potential energy, and that's the starting point. That's where the negative sign shows up, and then it's in everything. Basically, it also shows up in the definition of electric potential. Delta V has a negative sign on it, like this, right? So that's the reason why. Do you want me to explain why this is true again, or?
No, that's fine.
Okay.
No.
All right. For anybody else that doesn't remember, the idea is that when the force does work, it generally takes the object to a lower level of potential energy. For example, when a ball rolls down a hill, gravity is doing positive work on it, but the ball is going from a high potential to a low potential. So, all right. Yeah, that's basically it. I guess the only other thing to do would be to go back to this step and take the derivative of this with respect to x, and then doing the solution, we might as well at least try that. Let's see what happens. So if we wanted to find EX before we took the limit, then it should work to just take the negative partial derivative of that expression right there. This is one of those chain rule things, right? Take the derivative of the outside, derivative inside. So I'm going to write it in a way that I can explain it more quickly, I guess. So if we write it like this, then the derivative should be, bring the negative 1 down in front, so we'll have negative 1 times negative 2 KQA. And then we need to multiply this by the derivative of the inside, which would be 2x. Did I do that right? I am really rusty on calculus sometimes, because it's just been a long time since I've just done calculus problems. But does that look right?
Yeah, just the exponent. Subtract 1 from the exponent.
Oh yeah, this should be negative 2. Thank you. That looks correct. I mean, it looks like the same answer we got in the past. So negative 1 times negative 2 will be 2. There's a 4 right here, so we're going to have 4 KQA x divided by there we go. And if we take the limit of this, it will definitely give us this. And I left off a negative. Did I leave off a negative sign? I did, because I never used this one. I'm so bad at this stuff, I apologize. Negative of this. Which means there's another negative sign here and there's another negative sign there. There we go. So this would be the answer for the x component of the electric field at any point on the x-axis. So there we go. You have any questions? So I started class off with this problem today. For one thing, it's a simple problem that we can go through and solve. But it's also because one of the, I think, harder parts of the lab manual homework involves solving a problem like this. And I just wanted to kind of clarify some of the stuff that I expect that I want you to show in that problem. So the problem is, I think it's 379. And it's a little harder because you have to find the electric fields at an arbitrary point up here. And then, well, yeah, that's what you have to do. So I just wanted to talk about some of the things that are going to show up when you do that. So I'm going to draw another picture here. Bring this down some. So the problem you're going to do, let's draw like what do we need? We need like axes, right? This is probably fine. Okay, so we need one more line that goes this way. All right, the problem that you have to do, I think the positive charge is on the right side in the problem you do. Maybe I'm wrong. So you've got a positive charge here, and you've got a negative charge over here. Put them roughly equal to each other. I don't remember in the problem you guys have, what's the distance? Is it L over 2? I think it is, right?
It is L over 2. Okay. I got it right here.
So this is L over 2, and this is L over 2. And then it wants you to find the electric field. So what does it say exactly? It says to find the radial and the angular component, basically. You need ER and E theta. That's what you're looking for. I can get that problem, I guess.
With a little algebra of the same kind as in part A, it can be shown that the radial E field, E sub r, and the E field perpendicular are E sub theta.
Yeah, so it's ER and E theta is what you have to find here. Okay, so I don't know how comfortable you all are with like radial vectors and then like r hat and theta hat and what that might mean or what the angular direction is. So I just wanted to kind of clarify it all on this picture. So we need to draw a few more lines. We want to find the electric field at this location. So what we're going to do is we're going to draw lines from each of the charges. So we're going to need a line from this one to this one. And we'll need another line that goes from the positive charge up to here. And I should probably label that this is plus Q and minus Q. So the red one is positive Q, blue one is negative q. All right, and we'll need to draw one other angle on here, or one other line on here, because I think I found it to be pretty helpful when I did this problem. All right, I'm actually gonna have to pick a problem. Does it define this angle that I just made to be theta? Is that what it does? Then you have to have some kind of theta that's defined, right? Yeah, it does. Okay. So this angle that's down at the bottom is theta. All right. So for each of these charges, there's going to be a vector. It's going to be our electric field vector. So for the red one, that electric field vector is going to point basically parallel to the line that we just drew. Try to make this parallel. And it's going to point away. Should I make this bigger? I should at least make this line longer, right? That's definitely important. I have to make it straight again. Okay. So we got that one. And then for the negative charge, how should I draw the electric field vector?
Towards the...
Yeah, pointing to the charge.
Yeah, you basically go this way. They should be about the same length, but one of them is technically going to be bigger, right? Which one will be bigger?
The positive q.
Positive one, yeah. So, okay. So basically what I've drawn here, these are vectors. I'll label what they are. So I'm going to call the one for the positive charge E plus. I think I can write it right here pretty safely. Need this space. So that's the E plus vector. And then this is going to be the E minus, the electric field for the negative charge. Okay. All right. So those are the directions of the vectors, but it wants us to find a radial vector and a theta vector, right? So what we need to do now is to basically have those kind of axes drawn on top of here. And to get that to happen, I basically just need to, oh boy, where's that going? I just need to extend this line, like this way. Because this is the, what direction is this line going to be pointing in if I do this?
The theta direction?
So I drew a line basically from the origin out to this point, right?
Oh, it's the radial.
Yeah, so this is the radial direction, basically. Call that the r direction. The theta direction is basically perpendicular to it. So if that's r, then theta goes this way. So that would be positive theta in that direction, perpendicular to it. It's like, you can think of it as, you know, when we measure angles, we measure them usually counterclockwise from the x-axis. So the positive theta direction is counterclockwise from the x-axis, like that. So now we just need to break up each of these vectors into these components. So let's do that. Yeah, we use different colors so that they kind of stand out. So for the positive one, you're going to have a component that goes this way, and then you'll have another component that goes straight up this way. And this one right here is going to be, we'll call it E plus R. And this is going to be E plus theta. Boy, using the positive there's kind of kooky, but yeah, anyway. And there's going to be an angle inside of here. And the angle is, I'm going to call it phi. So this angle right here, I'm going to call it phi. Okay, on the other side we got to do the same thing. So let's use yellow, I guess. So for the negative charged electric fields, we're going to have a component that goes back like that. And then we're going to have a component that goes perpendicular to it, like this. And those will be respectively E minus theta and E plus theta. So then from here, and then it defines this distance as R, right? I forgot to put that on there. This distance right here is R, right? Okay, so I have to think about how much I actually want to solve this problem. So if that's phi, then this angle's phi, right? Yeah. So basically, here's what you have to do. For, let's say, I'll start off one of the calculations, because you still have to do a lot of work even after you've done it. So for ER, what we need is we need this distance between the positive charge and here, because our electric field is going to be K times Q divided by whatever the distance between the positive charge and this point is. So what I normally do is I call this R plus. And then you don't have to do this. You can pick whatever. You can call it R and R prime, and you can call it whatever you want to. And then I'm going to call this side of this triangle over here R minus. So basically, this really acute triangle, we have R plus, R minus, and R in the middle. So the electric field in the R direction is going to be KQ over R plus squared. And then we also have to subtract this vector over here. Well, I'm not quite done yet, actually, am I? KQ over R plus squared, but we also have to multiply by what? If we want just the radial component of this thing up here. If I just want this piece, I have to use a trig function, right? So I have to multiply by what? Sine or cosine of phi?
Cosine Phi.
Cosine.
All right. And then the E minus points back this way, right? So we're going to need this piece down here. And so we're going to have minus K times Q. It's a negative charge. That's where this negative sign is coming from. Divided by R minus squared. And then multiplied by, there's another angle now. It's not the same angle as this angle. What do we want to call it? Maybe alpha or something like that? Call this angle inside of here alpha. So then this is multiplied by the cosine of alpha. So this is kind of the starting point for proving. So I guess I'm not being really clear about what I want you to show. So it says, as Cam read, that with a little algebra of the same kind as in A, blah, 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 you can show that ER and E theta are given by those expressions, right? So you have to actually show that if you want to get full credit for this problem. That's basically what I'm saying. You need to actually show where those things come from. There are multiple ways to do it. So I'm showing one way. Another way that I've seen people do it, which may or may not be easier, I don't know, just depends on what you prefer, is you could also find the electric potential at that point, and then take the derivative if you want to. But you'll have to go look at what the gradient looks like in spherical coordinates. No. Yeah, spherical coordinates, right? Polar coordinates. And you can find that in your lab manual if you want. You can find it really in any math textbook too. But anyway, so just trying to show you kind of how to start this. So the biggest thing here is now you need to get everything in terms of, what is it? Basically K, Q, L over 2, and theta. And that's it, right? Oh, and R. So basically everything has to be in terms of theta, R, K, Q. I think that's it. They use P, but I think P is equal to, what is it? It's equal to 2 QL or something like that, right? Yeah. Oh, that's the other variable then, is L. That's the other variable. But you get rid of Q and L for this P variable. Okay, so how are you going to do that? What do you all think? I know I just threw a bunch of stuff at you, so it takes some time to digest it, but how am I going to simplify this equation to get everything in terms of those variables up there?
Well, first thing that came to mind was like trigonometry with this triangle that you've drawn.
Right. What do we do? It's not a right triangle, so we can't just use the...
Yeah, it's not right at all.
But that's okay, because there's rules for non-right triangles, right?
Yeah, there's the cosine law.
The cosine law, exactly. So we have cosine phi that shows up here, right? And that cosine phi shows up in this triangle that has theta down here, r right here, r plus here, and then there's the phi, right? And then the other side is L over 2. So you can use the law of cosines, for example, to say that within this triangle, I might get this wrong, but basically it's something like, I think, so there's two things we got to write down here. We need to write down an expression for r plus, and we need to write down an expression for cosine phi. So I'll try to write this down. I think this is right. So it's going to be something like r plus squared should be equal to r squared. Is it plus or minus? I think it's plus, right? Plus L over 2 squared. And then here, I think it's
minus 2a, or minus 2r L over 2.
So now what we need is 2 times, it's going to be these two sides. So 2 times r times L over 2. And then you have to multiply by the cosine of the angle that's opposite this variable, I think, right?
Yeah.
Which in this case is theta. So I think that's right. This negative sign, though, it may or may not be wrong. Let's go look up the law of cosines.
Well, if the theta, or well,
yeah, you're going to say if it becomes greater than
it becomes
180,
90,
or if it becomes like obtuse, it's going to be it's going to automatically make it negative. That's what I was thinking about. Law of cosines. So C is equal to a squared. Yep. Okay, we got it right. Looks like it's right. Okay. So that's r plus squared, right? That's going to show up right there. And then we need to do a similar expression, but we need a phi out of it, right? So for the phi, to get cosine phi in there, we'll need to use this expression. I think L over 2 squared should be equal to the other two sides, which would be r squared plus r plus squared. And then minus 2r plus cosine of phi. So that gives you cosine phi right there, right? Because you can solve for this piece. You can plug it in here. Yep. So this is the kind of stuff you got to do. It's not easy.
Mm-hmm.
It takes quite a bit of time. But if you're really careful with it, everything will work out. You'll get exactly the same answer they get. Okay. I'm not saying you have to do it this way, but it's just one of the ways you can do it. The other thing I'm going to say is that pretty commonly I will see people use a solution on this problem where they draw the vector for the electric dipole P. They basically draw the P vector, which goes from here to here. And then they do some kind of like math with it. I'm just going to say, like, if that's the method you're going to use, I'm going to put a pretty high demand on my expectations of how you solve the problem. So if you get to the right answer by using a method that involves basically drawing a P vector here or drawing a P vector at some angle this way, and that's how you solve it, you better be sure that you can explain every single step that you made. Because if you can't, then I'm just going to give you 0 credit for the problem. Well, at least for that part of it. So I say this because we'll leave it at that. Anything that you do on these lab annual problems is going to be heavily scrutinized. So if you do some mathematics that don't make sense, or if you make some assumption about what I know and you don't explain it to me, then you're not going to get credit. So just please take it seriously. There's so little of a way to really evaluate you as students in this kind of pandemic situation. And this is just one of the only things that I can use to evaluate you, is like how well can you fully explain something on a piece of paper.
I wonder what you even do for a dipole.
Me too, dude. I've seen people try that solution loads of times, and they all look the same, and none of them explain it to me. So you can take that for whatever you want to take it for. I'm not saying people are cheating, but I'm saying that they're just putting a solution down that they don't understand, so they can't explain it. And then I look at it and I'm just like, that's not an explanation. It's like it's like magic, basically. But hey, if any of you want to be the first one that can actually write it down in a way that explains it to me that makes sense, then go for it. Now, again, this is probably the harder way to do this. It's probably the harder way to do this. But you can you can do the version where instead of finding the electric fields here, you find the potential, and then you do basically what we did in the last problem right here. So finding the potential is a little bit easier because you don't need to do this vector stuff, and I don't think you even need to know what these angles are because you don't need angles for the potential. So you would just say, okay, well, the potential at this point would be kq over r plus minus kq over r minus. Then you'd still have to write this out for what r plus and r minus are. But then what you could do is you could say the radial component of the electric field should be equal to the negative of del v del r, right? And then I think the theta, okay, I might get this wrong. I have to go look this up, but for the theta one, I think it's negative 1 over r del v del theta. I'm almost certain that's what it is. This method is probably the easiest, but it still has some of the same features as the previous one because you're going to end up taking the derivative of something like this in the denominator that has an r right here and an r right here. And then same thing for the theta. You're going to have to take the derivative that's going to have this cosine theta, and it's all going to be in the denominator down here. So there's still quite a bit of mathematics to do. So doing it the way that I'm saying right here is like kind of like just the pure geometry method. Doing this method, you'll get to kind of use some of your calculus skills. So if you're more comfortable with calculus, you'd want to do this method probably. And if you're more comfortable with geometry and algebra and stuff, you'd probably just do this method. Of course, you can try both, and you should get the same answer either way, but you already know what the answer is because it's given. So yeah. Okay, I've said a lot of stuff. Does anyone have any questions about this? Be sure to use rulers and stuff when you're drawing all your diagrams for your homework. If the diagram is not very neat, I'm definitely going to dock points for that. So that means use a straight edge for everything. And yeah, that's pretty much it. I think the rest of the problems... Have you all been working on these at all? Like, as I'm sure some of you have, but...
I have.
Is everybody doing okay on those problems? Does anyone have any questions about them? Like...
I think the first problem was kind of similar to that derivation we did in class last week, right? About the line of charge.
Right. Yeah.
Okay.
And if you haven't done it yet, I appreciate you being honest. You definitely want to get started. The problems will take a little bit of time. There is one other thing I wanted to mention about those problems too. Something that I forgot to mention in class. So the other thing is so for Gauss's law problems, so Gauss's law says that here I'll write two integrals here. The surface integral of E dot dA gives you flux. I'm sorry, there's a phone call. All right. So the surface integral of E dot dA is equal to the charge enclosed within your Gaussian surface divided by epsilon naught. The one thing that I forgot to tell you about is that if you have a charge distribution that's like a function, which I know you have in one of the problems, then in order to find the enclosed charge, you need to do this. So you need to do a volume integral of rho dv. So the problem that I'm thinking of where you're going to have to use this is the problem where you're given, I think it's a cylinder, right? And it tells you that the charge density as a function of the radius is given by something like, is it r over b squared? Or r squared over b squared or something like that? Times rho naught or something like that? Is that right? If none of you have done this problem, I'm kind of...
Which one?
Yeah, I got it. That's right. 275. I'm looking at 275.
Okay, yeah, what about it?
So it gives you this charge density as a function of the radius, and you're going to have to use this expression right here. And on that problem, what you have is basically you've got a cylinder, and the cylinder's charged. And I think it's an infinitely long cylinder, right?
Mm-hmm.
Yeah, okay. So it goes up and down forever. And what you need to do, so it's basically just continues like this, and it's, you know, filled with charges. And the charges are basically all throughout the interior. So they're not just on the surface, because I guess it's an insulating cylinder. Yeah, non-conducting, it says. So what you need to do is you need to draw a Gaussian surface. Now, we did a problem where we had a line of charge that was infinite. This one is a cylinder of charge. It's really not any different. So for example, if I wanted to draw a Gaussian surface for the region out here, I can just draw one big cylinder that goes around around the object. And that's going to be my Gaussian surface on the outside. And for that one, it should be pretty easy. The one on the inside is a little trickier. But, you know, if I want to find the electric field on the inside, I'm just going to draw a Gaussian surface that's going to be inside of here. And it will enclose some fraction of the charge, right? Now, in order to calculate exactly how much charge is going to be enclosed in such a Gaussian surface, and let's say that we define the radius of this thing to be capital R or something like that. I believe the radius of this is B, right? Yeah, the total radius of the outside part is B. So what you got to think about is, like, I need to sum up all of the charge that's inside of here. And what I know is that the charge density is a function of the radius. That means that if I did a really skinny cylinder in here, I wouldn't enclose very much charge. But then as I expand out, it kind of geometrically grows in terms of the amount of charge that's in there, because it grows as R squared, right? Okay, so what you need to do is you need to think about this term right here, dv, and what it means. So when I want to do an integral, it's a triple integral, dv, then you need to have kind of an idea of what a dv means. Dv means an infinitesimal slice of volume of my object right here. So what that's going to look like, I'm going to show you what it looks like from the top down, because I don't think I can adequately show you. So if this is the top of our cylinder right here, right? And it contains all of our charges and stuff like that. So we're looking at the top of the cylinder now. So what we need to do is we need to basically construct a thin, I'd call it like a tube. We're basically going to construct a tube. And the tube is going to be inside of here. So it's going to have an inner radius like that. And then around that we'll have another tube that'll just be slightly bigger. Like this. So like think of concentric circles. Like that. So that thing is going to be a little hollow tube looking thing, right? Can you all envision what I'm talking about? It's like a big roll of paper towels, and this is like a tube that goes through the middle. Now you need to have a couple of variables on this thing. So this is going to be the radius. You're going to have a thickness that's going to be dr. And then it's going to have a length as well. The length will go kind of into the page, so I'm going to leave that part off. So the length is basically going to be, you know, like the length here, basically, or something like that. So we can't see it, but it's on the picture here, right? So then what I would say is that this thing, this little tube that we've cut out here, it's like a little, that's going to be our dv. Just indicate that. That's dv. It's going to contain some amount of charge dq, right? But now we just need to say what dv is, okay? And it's a geometrical object that has a radius r, a length l, and a thickness dr. So basically what we can do is we can say that dv, does anyone know what it would be? This is purely just geometry. It's basically, I give you a little tube, right? And I'll just draw it over here. It's a little paper towel holder. Again, so thickness dr, length l, the radius is r, and then, yeah, I can't really draw the thickness of this thing is going to be dr. What would the volume of such an object be?
2 pi r L dr.
Yeah, and Henry also wrote that down in the chat. That's exactly right. So 2 pi r will be the circumference. We need to multiply that by the length. And then we also need to multiply by the thickness, right? That's the other dimension. Okay? So with that and that, you can do this integral now. And the integral will reduce down. I'll just write it down what it will look like, so in case you haven't seen these like triple integrals and stuff like that. The triple integral means you're going to take the integration over 3 variables, okay? In spherical coordinates, that would normally be... Oh, sorry, this is cylindrical coordinates, excuse me. In cylindrical coordinates, that would generally be an r, and then an angle, which would be phi or something like that, and then z, the z coordinate for the up and down direction, basically, right? And so, I don't know, if you take a class like this, you'll learn that the way you do these dv things is by using something called, what's it called? The Jacobian or something like that? Is that something you all have learned about before? Basically, there's a version of this dv that you would use for polar coordinates, for cylindrical coordinates, one for Cartesian coordinates. But I always found it I always found it a lot easier to just,
do that.
Yeah, to just think about it geometrically, because then you can do it for any problem, not just problems. Here, I'm skipping too many steps. So this integral is going to become just a single integral is what I'm trying to say. So it's going to be rho naught r squared over b squared. That's your charge density, basically. And then you multiply this by what we just figured out, 2 pi r L dr. That's a really easy integral to do, right? Really easy.
Yeah.
And you just integrate from 0 out to whatever the size of your Gaussian is or whatever. Or in the part where you're going to find the electric field out here, you just integrate from 0 to b. But on the inside, you integrate from 0 to something like r or whatever. So there we go. That's how you're going to find the charge enclosed. There's a lot of mathematics to get there, but I hope that is helpful to you in setting up the problem. Once you get past that hurdle, I think this problem is pretty straightforward. Things I expect to see on this problem are you're definitely going to want to show your electric field lines, what direction they point. You're going to need to show the direction of dA. In this case, the electric field lines are going to be kind of out, and dA is also going to be out. But I'll dock points if you don't show those things. But it's easy to draw. Try to make this diagram as neat as you can too. It's not easy. Any questions? I think those. Go ahead.
So for the problem, is it okay if I said, okay, since what I did is I found the ring of charge, the flat ring of charge, and then I was like, okay, since it doesn't depend on the axial length, then you just multiply by L. Because it's only radially dependent.
It's the same thing, yeah.
Okay.
Yeah, if you did this calculation and there wasn't an L in here, and then you multiply by L at the end, I guess that's okay. It's not really the best way to do it, but it's okay. It's fine. Any other questions? Yeah, if you haven't tried these problems, I'm sure that what we're going through right now is just like going way over your head. But it's recorded, so when you actually do finally get the time to sit down and try them, and then you run into a difficulty, hopefully you'll come back here and use some of these hints. I assigned 278 to you all as well, right? This thing with the ring and the electron.
Yes, you did.
Did we already talk about that? It's been a while.
No.
Well, for that problem, excuse me. For 278, you're just gonna have to maybe go back and review some simple harmonic motion stuff. So I'll just write that down.
I do have a question about how I...
Go back and read Simple Harmonic Motion chapter and understand what a restoring force is, how we use it to find frequency, and you should be able to compare it to this problem because you just replace the restoring force from springs, which is kx, with the expression that's given or that you calculate. It's really easy. You can solve it really quickly. So simple harmonic motion, that's what's going on. Go back to the chapter, which is chapter 14 or 13 or something like that. Or just go watch a video about simple harmonic motion. Primarily the derivation. The derivation of where you go from the force equals mass times acceleration down to the differential equation that you get. Because you'll be able to get something really similar for yours. Okay, wait, was there something else you said?
Yeah, for that question, I found the equation, and what I did is I compared the coefficients to to the general simple harmonic motion equation.
Exactly.
And then I said, oh, from this, then the period must be, and then insert coefficients here.
That's right. That's exactly right. Yeah. You just compare the two equations. You look at yours. You look at that one, and you'll notice that there's going to be a k in the simple harmonic motion equation, and you're going to have a whole bunch of stuff, basically. That's going to be what your K is, basically, that'll show up. Okay. Hopefully that's enough to get you all set up to succeed on those problems. It's 2:47. I'd like to at least do this problem today, so let's do that. All right, so shifting gears, back to doing a problem. We have two connected charged spheres. So two spherical conductors of radii R1 and R2 are separated by a distance much greater than the radius of either sphere. So basically you've got a spherical shell, a spherical conductor, it's not a shell, spherical conductor, and then a wire that's also a conductor that separates them. And the wire is just really long, basically, is the idea. Okay, the charges on the spheres are in equilibrium, so that's important. Are Q1 and Q2 respectively. The idea would be if I were to add a little bit more charge to this one, that charge would tend to basically spread itself equally out or proportionally out between these two spheres. So we're at equilibrium, and these are the values of the charges. We want to find the ratio of the magnitude of the electric fields at the surface of the spheres. So basically, near the surface of Q1, you're going to have electric field lines that go out like this. We'll call that E1. And then the idea is that the other object is really far away, so that the electric field lines of Q1 aren't going to affect it. So this is going to have some electric field that we'll call E2. And because they're spheres, it's going to be kind of your normal radial electric field that you get. All right. And the fact that they're equilibrium is also important because we can use some of the conditions for conductors in electrostatic equilibrium to help solve this. All right. So our goal is to find the ratio E1 over E2, what it's equal to. All right. So this problem is going to allow me to kind of say some things about electric potential that I haven't said yet, that I know for a fact are going to be problems that you're going to have show up on your homework, okay? So let's talk about that first. So if I have a conducting sphere, or any kind of conductor, basically, it doesn't really matter if it's a sphere or a ring or whatever, and it carries some charge Q, right? Then what I can say is that we said before that we know automatically what the electric field inside of this thing is if it's in equilibrium. What's the electric field inside?
Zero.
It's
0, exactly. So what we'd like to know now is, what do we know about the electric potential? Now that we know, So in general, I don't think I've talked about this enough, and I probably should. Suppose I have a system where I know that at one location, the electric potential is 0 volts, and nearby the electric potential is 1 volt, and over here the electric potential is 2 volts. All right.
Mm-hmm.
And I tell you that I place a charged particle that's positive right here, a positively charged particle Q. What direction is the force that it's going to feel?
To the right?
To the right?
It's going to go to the lower potential.
Why would it go to the lower potential?
Objects they have high potential, and then their potential is released into kinetic energy, and they move to a lower potential.
Right. So if you're not understanding what electric potential is, what he said is exactly right. You can always immediately compare it to gravity, okay? So with gravity, you can either use altitude or you can use potential energy. It doesn't really matter. Let's use altitude. So let's say that this has an altitude of y equal to 5 meters, and then I make little grid lines to represent each meter that an object could roll down a hill, right? So this is going to be y equal to 4 meters, 3 meters, 2 meters, and 1 meter. Okay, now I'm going to ask what is effectively the exact same question, and I know you all know the answer. I place a ball at this location here, right? Does it go from high elevation to low elevation, or does it roll up the hill if I just release it from rest?
It's from high to low.
Yeah, right. You always go from high to low. So that tells us something about positive charges. Positive charges basically tend to move from high electric potential or high voltage to low voltage. It's a kind of hill, right? It goes from high to low. So the force, as Cam was saying, on this object goes this way, right? Now, similar to these lines that I've drawn here to represent altitude, we can also draw lines to represent places where the electric potential is the same. We call these lines equipotentials, okay? So if I draw a line like this and say it's 2 volts, and then I draw a line like this and say it's 1 volt, and a line like this and say we call these lines equipotential lines. Or just equipotentials. And all along that line, the voltage is the same, okay? What that means is if I place a positive charge here, for example, and I try to move it in that direction, parallel to the line, the electric field will do no work, basically. It'll do no work. It will do work if I take it and I try to move it from 0 to 1. It's going to resist that because, as I said, positive charges want to go down. They want to go downhill, basically, right? Down to the lowest possible potential. So if you try to move along a potential line, your potential doesn't change. That's like if you have a flat surface and I try to roll a ball in this direction, gravity is not going to slow it down, right? Gravity has no effect on a ball that moves left and right on a table. It just keeps it on the table. And then, of course, it modifies the friction force too, right? But gravity itself isn't going to resist your motion to move left and right on a table, right?
Just like an altitude contour map.
It's 100% exactly like a contour map. Yeah, exactly. Okay, anyone have any questions? Okay, so given all that stuff we just said, let's come back to the sphere. So this sphere here, I'm saying, is a piece of metal. It's a conductor, and it carries some charges. It's in equilibrium, and I'm saying the electric field inside is 0, right? Okay, so what do we know about the electric potential inside then?
It's gotta be constant.
Has to be constant. That's exactly right. So if it weren't constant, and I told you that this point on the right was at a higher electric potential than this point on the left, that would imply that there would be an electric field line that would go between these. It turns out that electric field lines are always perpendicular to equipotentials. Okay? Electric field lines are always perpendicular to electric potentials. So if we know that the electric field inside of here is 0, then it's impossible that there's any potential difference between these 2 points. So that means that whatever the electric potential here has to be the same as the electric potential here, and you can continue that line of thought all the way out to the exterior of the object. Basically, when you have a conductor in electrostatic equilibrium, whatever the value of the electric potential is out here, it's the same inside of here. So if the electric potential out here is 10 volts on the surface, then the electric potential inside is going to be 10 volts all across it, okay? Now, this applies to a couple homework problems that you have. One of the homework problems that you have involves a ring, and it's a charged ring, and then I believe that there is another ring that's inside of it, right? There's basically 2 rings. So it's going to ask you to calculate the electric potential at various points within the system, out here, here, and here, basically. And what you need to know is basically that if you know what the electric potential is at the surface right here, it's going to be the same as the electric potential on the inside. Okay? Now, when you get outside of it, the story changes, okay? So if this is Q1 and this one's Q2, when you're out here, if I define this distance to be R, okay, then the electric potential at this location is going to be K times Q1 plus Q2, I think just divided by R, basically. But when you get inside of it, the electric potential is equal to the value of the potential on the surface. Okay? So if you can calculate what the electric potential is right here, you can find what it is inside. Do you all know which problem I'm talking about? Has anyone tried to do that one yet? Anyway, you will eventually. People will have questions. There's the answer. Hopefully that's kind of helpful. All right, so now we can take this idea that the electric potential has to be constant to say that if I have a conductor, like this one here and this one down here, the electric potential has to be the same everywhere. And the fact that there's a wire that is drawn between them guarantees that the electric potential in this entire system has to be constant. So, what's it equal to? For this one right here, if I were to come right out here to the surface to figure out what the electric potential is, I would say that the electric potential at this location should be equal to K times Q1 divided by R1. You might ask, oh, why don't I have to write anything for this? Well, remember, this is supposed to be like really, really far away from this one. So it's not going to affect the electric potential. For the lower object here we'll call this one V1. The electric potential down here, V2, I thought I'd switched markers. Green, okay. It's going to be V2 is going to be equal to K times Q2 over R2. And that will be the value of the electric potential. You know, this kind of looks bad because of that E2 that's sitting right there. We'll just write over here. V2 is equal to K Q2 over R2. Now that's the value of the electric potential at the surface. If you go a little bit farther away, you would have to use the R, the distance away. But if we're on the surface, then that's what it is. And that ends up being the same value at any point inside of here, basically. Okay, if we read what it says down at the bottom, two charged spherical conductors connected by a conducting wire, the spheres are at the same electric potential. That wire forces them to be at the same potential. Okay, so now what we do is we say, if those are the same, that means that V2 is equal to V1, right? Which means K times Q2 over R2 is equal to K times Q1 over R1. All right, we'll use this equation here in a little bit. What about the electric fields? Well, to find the electric field, it's pretty easy. The definition of the electric field, E1, if we look just at the surface, because our goal is to find the ratio of the magnitudes of the electric fields at the surface. Right at the surface of E1, the electric field is going to be K times Q1 divided by R1 squared. And the electric field for 2, K Q2 over R2 squared. And our goal here was to find a ratio of E1 to E2, right? So what we'll do, let's go down just a little bit here. I don't really have room to go down, do I? Let's just start writing it over here. So if I want to do E1 over E2, this should be equal to, if I take these and divide them by each other, the k's will cancel out, and we'll get, so R1 is going to be in the denominator, and R2 will be up here in the numerator. Now is where we can take advantage of this piece right here. According to this equation, if we cancel out the k's, this is the electric potential equation, it tells us it tells us basically what the ratio of Q1 over Q2 is, right? It says basically that Q1 divided by Q2, so just take this Q2 and divide it here and take the R1 and move it up here, should be equal to R1 divided by R2.
Interesting.
Now this relationship should make some kind of a sense. What this tells us is that basically the ratio of the amount of charge on the spheres when they're in equilibrium is proportional to their radii, how big they are, right? And the object that's bigger is going to carry more charge. That should make sense. There's just more room for the charges to spread out up here, right? So this is reasonable. And now all we need to do is just replace Q1 over Q2 in this equation. So we get E1 over E2 ends up being equal to R1 over R2. That replaces Q1 over Q2, multiplied by R2 squared over R1 squared. So then one of these cancels out. What are we left with? R2 over R1, right? So that's the answer. This is the ratio of E1 over E2. It is inversely proportional. Is inversely proportional to the radii, right? So according to this equation right here, which electric field is bigger? Is it E1 or E2? And if it's hard to read, let's just say R2 is equal to 3 and R1 is equal to 1 or something. Oh, no, backwards. So then R1 would be like 6, let's say. Which one's bigger? If we use those values, this equation would say E1 over E2 would be equal to 3 over 6, right? Or 1 over 2. Yeah, E2 is bigger, right? According to this, it's twice as big if the radii are like this. So if you have a smaller radius, you get a bigger electric field, right? Even though Q1 has more charges, or more total charge inside of it, according to this equation. In fact, Q1 actually has twice as much charge, right? If we choose these numbers. In spite of all that, the electric field for 2 is still twice as big. So what does this tell us? This
That
go ahead.
something to do with the charge density?
Yeah, it's related to the charge density, absolutely. In fact, we know another way to write E2 would be to say that it's equal to the surface charge density divided by epsilon naught. That's another way we can do it. So probably the surface charge density for the smaller one is just it's a lot bigger, basically, as you said. It also tells us that if you have an object that is curved in some kind of strange way, the place where the object is the sharpest, or the place where the object has the smallest radius of curvature, is going to be the place where you get the biggest electric field, which also means that's the place we're going to get the biggest kind of shocks. So, like electrical shocks, basically. So what do I mean by that? I mean that we talked about this last Thursday, I think. So if I have an object that carries charges, and let's say that it's kind of roughly smooth like this, but then it comes like to a point, to like a really, really sharp kind of point like that right there, and it carries charges. So what happens is that the charge density in the region where it's really sharp is going to make it so that the electric field is going to be the biggest right at this sharp point. So electric field is biggest at sharp points, right? Because if we were to model pieces of this with spheres, then if I were to come to this piece right here, do you guys understand, have you heard of the idea of like a way to measure curvature by using a kissing circle? Have you ever heard that expression before?
Yeah.
The idea is that if I want to figure out the curvature of this little piece right here, what I want to do is just draw a circle with the biggest radius that I possibly can, such that it only touches the surface at one point. And then you can define the curvature as being related to the radius of this circle. Okay, so I could draw a really big circle here, and it might only touch this portion of the conductor at one point, right? But if I want to come into this really sharp point right here, I'm going to have to draw a really tiny circle. Okay, and the curvature is inversely proportional to the radius. In fact, I think it's inversely proportional to the radius squared, but that doesn't really matter. The point is that it's related to this radius right here. So if the radius is big, you're talking about a flat surface. Think about the Earth. The Earth has a massive radius. It's so big, it's 6,400 kilometers or whatever. It's so big that the surface of the Earth basically looks flat, right? If you're on the surface of the Earth, if you can't actually see the curvature, if you don't go outside of the Earth to where you can really see the curvature, the surface of the Earth basically looks flat. And to a good approximation, it is flat because the radius of the Earth itself is so incredibly large, right? But things like this little sharp point right here, you'd have to draw a really tiny circle, and the tiny circle means that it's a big, really high curvature at that point. Okay? So, electric field is biggest near sharp points. That's also the place where you're more likely to get shocked, basically. Okay, anyone have any questions?
It's interesting though, like also if you have a whole system of these connected conductors,
Yeah.
and you know the radius of one and like the electric field at one, then you can find well, I mean, you could find the electric field of another part of it as long as you know its radius too, I guess.
Yeah, I guess, yeah, if it's a simple system like this, sure. Yeah. So a couple things come out of this problem that are important. One of the biggest things is just the understanding that by connecting two distant objects with a wire, it basically kind of equalizes the potential in a way. That's one thing. And then we learned that the electric potential inside of an object is equal to the electric potential on the surface, which should help you with this problem down here. And I think that's a pretty good place to stop for today. I'll stick around and answer questions, though, if anybody has them.
Professor, I had a question.